All right. Thanks for showing up, everyone. This is Take Flight with Elixir, and this is the Nerves Meetup Edition. So I did this presentation, I think it was a month or two ago for the Seattle Elixir Meetup. And we've got more of a software crowd over there, so I kept it kind of higher level and more of an introduction, kind of into nerves and into hardware. So I've replaced about half of this presentation specifically for all of you who showed up today. So we'll do more of a deep dive into like hardware and specifically shift registers and some of that fun stuff. So that being said, I've been playing this simulator for probably on and off for like 8 years now or so. I keep getting like hooked on it and coming back to it. It's a Digital Combat Simulator, DCS for short. And it's incredibly realistic. Like it's one of the most realistic flight sims that you can find out there that actually models everything. So like the cockpit that you see in the lower right-hand corner here, all the like buttons and knobs and switches, like almost every single one of those controls actually does a real modeled function in the sim. So it's just insane how detailed this is. Because of that, it's also really hard to map all of those controls just onto a joystick and also onto a keyboard because you have more controls than you can really touch. So the problem you face in the sim is you end up having to kind of like look around and click things with the mouse, and it's really cumbersome, especially since you like have to physically lift your hands off the flight controls when you're trying to fly to grab the mouse, and it's just a pain. So the vision behind this project was to move those important virtual controls out into physical controls that I can use in the real world and really just make it more practical to operate the aircraft and just have a better feel when flying the simulator. I'm by no means the first person to do this kind of thing. There's a bunch of like home-built cockpits and stuff. There's a community of people, out there who do this kind of stuff, and I've been kind of looking around at other folks who have been doing it, and hopefully this provides some evidence that this is a socially acceptable thing for me to do. I'm not weird. Other people do this. It's normal. So there's one person in particular who's started up a YouTube channel around a cockpit build around the same sim, and he's been doing this for a while. And here's a little screenshot of kind of his setup, and he's got videos of building this stuff on YouTube and all that. So for detailed videos of anyone who wants to see the build out, I highly recommend that. His system, though, is heavily set up around Arduino because it kind of works out of the box with a part of the system I'll show you in a bit. But this being the Nerves group, of course, we've got to use Nerves for this project instead of Arduino, right? So that was my big challenge around this, and one of the things I wanted to shoot for. So this is the prototype of the setup that I've got going right now. And let me turn on the little pointer here. A lot of it is kind of prototyped out on this left-hand side panel. I've got a close-up of that. There's a little bit of it creeping into kind of the front panel here that's tethered into it. And I've got a right-hand side panel that I need to build out. But you can kind of see like things from the sim itself are kind of mirrored over to the controls. And if you flip switches and move buttons here, they actually change in the cockpit too. So pretty cool so far. So my name is Alex. You can find me at A.McLean on the Elixir Slack or also on GitHub. I'll dive into the system a little bit here. I already mentioned the software DCS. That's kind of the application running on the computer that you're actually flying in. There's two other parts of the system that go along with this. There's what I'll call an interface layer, which is how you bridge the software to the hardware. So there's a third-party program called DCS BIOS that somebody else has made. It's open source, and it essentially runs as a plugin inside the software because they support a plugin model. And it's a little kind of sidecar app that sits on top of that and exposes out some interfaces for you to be able to connect hardware to. Then, of course, the other part of this project after that is the hardware side of things, and this is where I attached Nerves running a BeagleBone Black. It's also where people traditionally attach like Arduino devices to be able to talk to that. So going over DCS BIOS just quickly here, this is that software that exposes the simulator's controls externally. It supports a couple types of inputs to your hardware, so you can do like serial port communication. So like Arduino exposes like a virtual serial port, so it can detect that. It also gives you the options of doing Ethernet via TCP or UDP. So that's a really cool option, and especially for running BeagleBone, I leveraged that. These controls also have well-known names and values that you can use for each aircraft. So for example, up here you can see AHCP Alt SCE. That's a special little string that we can use from the hardware side to be able to talk to this particular control and set its values and stuff. And DCS BIOS here is also accessible via a web UI, so that makes it really helpful to go in and debug bidirectionally to be able to see what a command might be set to, or like move one of these sliders and also set some values and see what happens. The other thing they give you down here is snippets of Arduino code for each one of these controls, but of course in the Nerves world that didn't help me very much, so I had to build a little bit of that from scratch. Moving on to the hardware, here's that left-hand side panel. So I've got the BeagleBone Black up here running as the controller, and you can kind of see the Ethernet cable going off to the computer there. As is tradition in a hardware project, I've got my rat's nest of wire here bridging everything together. And that's just connected to all of the buttons and switches and knobs and all this stuff on the panels here. So I've got some plans I'll show you for cleaning this up in the future, but that's kind of what the prototyping of this ended up being like. And I've still got a couple little components like some of the indicator lights here and some of the switches missing, but I'm working on filling those in as I can. So talking about the controller, like I mentioned, DCS BIOS is really designed to work with Arduino out of the box. I happen to go with a BeagleBone Black running Nerves. One of the reasons for that is it has a whole lot of I/O and peripherals available to it. So for example, if I was using like a Raspberry Pi, you get about, maybe like 2/3 of what this one particular header would be here. So for just number of I/O pins, BeagleBone has a ton of them, and I used, like you saw in the picture, a ton of them. So I kind of ran out at this point, so I'll show you some ways I'm looking at expanding that. The other cool thing about the BeagleBone is it's got a watchdog timer available on it, so I just wanted to throw that one out there. Cool thing about that is it will restart the device if the device crashes, which is nice when you're flying a simulator or airplane, because if your hardware crashes, you don't want your plane to crash with it. So I also had to build a custom nerve system that went along with this. One of the things was to expose additional hardware functionality. So like I said, I just needed so many I/O pins. Part of it was just being able to access more of the GPIO through those pins than the default configuration that was normally attached to those. I'll get into that in a bit. That's essentially the pin multiplexing part. Also needed access to be able to switch around the pull up and pull down resistors for the GPIO. So Circuits GPIO, that library, I believe does this out of the box for Raspberry Pi, but it does not do it out of the box for BeagleBone. So I had to do a little experimentation to get that to work. And as part of that experimentation, I needed to be able to use the config pin binary to kind of reverse and figure out what was going on and what it was calling and what it was doing. That didn't work out of the box with the out of the box nerve system. So in the custom nerve system, I just compiled in git opts, and everything was fine, and I was able to run config pin and figure out what it was doing. And I'll kind of get into the results of that in a bit too. As far as components go, because that was a gigantic part of this project, obviously, and I've heard a bit from folks in the meetup, this meetup before, of like, how do you go about finding components for your project? I think one of the ones before was like sprinkler components or automated valves or something like that. So I thought I'd mention that a little bit here. First of all the panels, I got a ton of those off of PC Flights, so that was a really cool supplier there. And then there's kind of the common component warehouses, DigiKey and Mouser. Those are two really, really good places to be able to find a bunch of different kinds of components. And then you've also got the more like hobbyist part suppliers, and you can find kind of like more pre-assembled circuit boards and more tutorials and help and things like that from places like Adafruit and SparkFun. So also really, really good resources there. If you haven't had to search for components before, you may end up encountering an interface like this. This is DigiKey search, searching for toggle switches, for example, and it can feel like you're just overwhelmed with just a whole lot of information that might not make sense when you're first looking at it, and this might look really intimidating. So I just wanted to put this in perspective and say, when in doubt, just ignore the features that you don't need or that you don't know about or that you don't care about. So if you don't select any of these, that's okay, like just ignore them. Focus on the ones that you do actually care about. So in the case of the switches that I needed like panel mount switches. So all I had to select was panel mount, and I can ignore surface mount and through hole and a bunch of these categories over here. Like I don't care about manufacturer, for example. Another important part, like if you only need an on and off switch and you don't need a three-way switch or stuff like that, then just select on and off. And leave the rest of the stuff blank, hit search, see what it comes up with, and you can kind of go back and refine your results as needed. And hopefully that'll help you narrow down the type of parts that you're looking for. That'll end up coming back with like this giant list like this, typically of different parts. One easy way to start sorting through this, especially for the hobby level, is start sorting by things, and a great place to start is by price, typically. So you'll start seeing just kind of in order a bunch of different components here. You can drill down then into each one of these. I'm not going to do this in the presentation, but you can drill into them either by the model number here, and it'll give you some information on it, or if you click the little PDF here, it'll pull up the manufacturer's data sheet, and that'll get into a bunch of the specifics about the part. So if you've got something that looks kind of close to what you're looking for, but it's not exactly right based on this search, these manufacturer part numbers, even though they might look a little cryptic, they are a specific code most of the time that describes different variants of this part. So the manufacturer will tell you in the data sheet, like this part of the part number means like it's a 2-position switch or a 3-position switch, or the size of the switch, or things like that. So if you go into if you find a part that's close to what you want, you can go into the data sheet and kind of decode these parameters and then build the part number for exactly what you're looking for that specific model. Plug that back into the like DigiKey part number search, and you'll basically get exactly what you need. So I'll dive into code a little bit. This group probably knows a lot about this. This is kind of high level, so I might skip past some of this. But one of the important parts here is the pin multiplexing bit, because this didn't really come out of the box with Circuits GPIO on the BeagleBone. So first of all, pin multiplexing is something that a lot of the ICs or microcontrollers typically integrate these days, because those microcontrollers have so much functionality built into the chip that there's more functionality than can actually come out the limited number of pins that are actually on the package. So a lot of the pins of each one of these like microcontrollers can do more than one thing. Sometimes they can do like 3 things or 5 things, like they can do a bunch. So you need to pick what you want the pin to do for your particular application. Especially like in my case where I needed a whole lot of GPIO. So I didn't need these UARTs, for example. I didn't need like these, the SPI bus and stuff like that. So I could turn these off and change these pins into being GPIO pins instead, to be able to get as many GPIO pins accessible on the device as I possibly could. So the first part of it, there's basically a part of the file system that you can write to that will tell you what the pins are configured to if you read from them, and if you write to it, it'll set what the pin is supposed to do. So that's over in this file path here under sysdevices. Whoops. And the magical part of this path is there are 2 pin headers on the BeagleBone. Let me just quickly go back to that. So you've got pin header, I forget which one's which, but one is 8. I think this one's 8, and this one is 9. Port 8, port 9. And if I go back to this chart, this is the chart for port 9 and what all those pins do. So the first bit of this file path is which port you want to talk to. The second, and it's all underscore separated. Second part of this is the pin name that you want to configure. And that's just a little formatting I'm doing up here of converting the pin just to a string and then padding it, because like pin 9 will be 09 on the file system, for example. And then the string pin mux. So this is a directory that you go into to be able to configure a certain pin on port 8 and what you want to set that pin to do. There's a file inside this directory then called state, and that's where all the magic happens. So if you read from this state file, it will tell you what that the function that pin is configured to do. So it might say like ADC, for example, out of the box, or it might say UART in the default configuration. Since I want GPIOs, I can write a value to this state file for the pin, and that'll change it to do something different. So in this case, I set it to GPIO, of course, and then there's this little part after it that says PU. And this is how I'm able to set the pull up resistor on this particular pin. So then if you wanted to pull down resistor, you could do PD, I believe it was. And this is the part that I had to use that config pin utility to try to figure out like where this stuff was and what the magic values were and things like that. So once I kind of figured that out, this became easy, but it was a bit of a pain to figure out where that was in the first place. You guys probably all know about GenServer, so I'm going to breeze through this part. But for just kind of for posterity, for anybody who might not know, GenServer is basically a dedicated process that can hold some state. It's started up by something externally like a supervisor or another part of the code. You get a little init callback where you can kind of set up the process to how it's going to run before it actually starts running. And then it goes into a receive loop of receiving messages and handling each one of those messages, doing something with it, and then kind of doing that over and over and over again until it shuts down. So I used one of these in the application to receive messages from Circuits GPIO to be able to understand which switches and stuff were being pressed. So here's the init handler. I'm going to breeze through this too. The two important things here is I had to configure the pin mux for each of the headers in the init. So just before I started processing things, I just made sure the pins were configured correctly. And I also opened a UDP port so that I could talk out that Ethernet connection as well. And I just held on to the handle of that in the init. I'm going to breeze through the circuits part 2 here, but basically just all the GPIOs that I needed to configure. I opened all of them in circuits and then just read the initial values from them so I knew what they were set to. And then I had to set up my own little scan timer that just pulled every 20 milliseconds just to see if any of those states changed. And this was just a really crude way to debounce this. In the circuits GPIO library, there is supposedly a way to be able to get notified. You can like set up an interrupt and be notified when that changes, but I've kind of had a little bit of trouble with that debouncing correctly. So I just set up polling and haven't had time yet to kind of go back and dig into that yet. So then on the handle info side of things, when the message comes in, I'm going to breeze through this too because most of you probably know about this. Circuits will send your GenServer a message, and that's how you can handle the circuits event that came in. Comes in with an atom just called circuits GPIO, gives you the pin number that was triggered. It will give you a timestamp that I'm just ignoring right now, and it'll give you the current value of whether this is like high or low, 1 or 0. I'm taking that and mapping it to a certain parameter. So this is that parameter that you saw back up in DCS BIOS. And so most of this program is just a whole bunch of these mappings of GPIOs to DCS BIOS parameters. I send this out the UDP port and I just also send the value that I want it to be as well. And down here, you'll see I'm sending it as UDP. I mentioned there were a couple connectivity methods with DCS BIOS. You could do serial, you could do TCP, you could do UDP. I thought I'd just briefly hit on why I did UDP, especially versus TCP. This is one of those things that might be helpful when you're dealing with like small embedded devices or embedded projects or anything that sends tiny amounts of data. So TCP has this handshake that it has to do at the beginning of the connection. So the client has to synchronize with the server has to synchronize with the client. They both have to get this agreement between each other set up, and then the connection is finally established. And once that connection is established, then you can start sending packets between the client and server. Every time one of these endpoints sends a packet out, the other one has to acknowledge the packet. The other catch to TCP is it likes to try to be efficient with the data in the buffer. So if you're dealing with small messages, like in this project where it's only sending a handful of bytes out, it's easily sending less than 100 bytes. TCP by default is going to try to queue these up to be more efficient with them. And it's going to wait either until the buffer fills up or until a timer expires, and then it'll send the packet out. There's a way to disable that with TCP no delay. It's also called the Nagel algorithm. So if you're dealing with smaller packets of data that are sent frequently, make sure you turn TCP no delay on so there is no delay, like it turns off that timer. So these get sent out immediately. But you still have to deal with the overhead of hacking and the handshake and all that stuff. So I went with UDP for this project. It's sending out really small datagrams, so it kind of suits this well. And there's no, you'll notice there's no handshake in UDP. You basically just get to send out a datagram, and it just goes from client to server. And the server just needs to be, listening on a certain port for this datagram to come in. If the server isn't listening, like you haven't set up your port to listen, the server's just going to drop these datagrams. And the other thing to be careful about with UDP is networks have an MTU, or maximum transmission unit, and it's typically about 1,500 bytes. And so if your datagram exceeds that MTU size, the network, typically like a network switch or so on, will drop your datagram and not forward it on the network. So that's kind of a trap just to be careful of if you're using UDP. Just make sure you're kind of respecting the MTU limit, and everything should be fine. UDP, since it doesn't have this handshake or it doesn't have this acknowledgement, it's also not reliable, that I'll use in air quotes, so it can drop your packets. So over the internet, this is why people stream like audio and video with UDP, because if you drop a packet, it doesn't really matter because the next one is coming so quickly that you'll get the data you need. If you're sending control system messages like over the internet, that could be something to watch out for, because you can't guarantee that reliability. So you might have to implement some extra checks if you're doing that kind of thing. But I've got like one hop on a local network switch right here, so my network reliability is pretty high, so this feels like a safe route to use. Next steps for this project, I'll breeze through some of these, and then we'll get into the shift registers. And also feel free, if you want to, feel free to be interactive through this. So if you got questions as I go along, or you want to comment on stuff, feel free as well. But I want to take this rat's nest and get it out of breadboards and turn it into a PCB or a couple PCBs that can interface all these cables up in a lot cleaner way to the hardware. So I've done this before with, there's various pieces of software for this. KiCad and Eagle are both great ones. So I've used Eagle a lot in the past. I'm really looking to switch to KiCad here. But if you go through this software, it's not too bad to use. These are probably more intimidating screenshots that I got from KiCad than would actually be to build a small project like I'm doing here. But it's kind of a two-step process. Build out your schematic in the schematic editor, and then place and route those components on the circuit board layout here. That'll generate a zip file for you that have some manufacturing files. You can take those into a service like JLC PCB or OshPark. Those are two manufacturers that'll make PCBs for you. This is a PCB of a prior project that I've done that I just uploaded here for a screenshot. And so you get a little preview of your board, typically, just to make sure that as a little sanity check, kind of make sure everything looks okay and nothing's like blatantly off when you're kind of getting it quoted. And PCB options here, which I won't go into, but I'll give you a resource here in a second if you're interested in doing this kind of thing. And they've got a little like live calculator, most of these sites do, that'll give you a live quote of how much it's going to cost. And spoiler alert, even though this one says like $2 for their discount here, like the shipping on it's probably like $20, but still not too bad. So if you're interested in this kind of thing, there's Dave Jones at the EEV blog spent like an hour in one of these videos just going through all of the options that you can choose from on JLC PCB and what they do and all that. So I highly recommend this video if you want to build a PCB or if you're just interested in it, because it's something that's probably a lot easier than you think. So I highly recommend taking a look at that. The other thing I'm going to point out, but I'm going to gloss over a little bit here, is exposing a USB joystick through this device as well, because if I want this to work with other simulators that aren't compatible with DCS BIOS, because obviously that only works with one piece of software, like if I wanted this to work with like Microsoft Flight Simulator or X-Plane or something like that, I can't use DCS BIOS to do that. I need to use like traditional something that looks like a traditional joystick to the operating system. So there's a way you can do this with config.fs, and I'm not going to go too much into it here. I'm just going to point out a couple of resources if that's something you're interested in, because I could probably turn this into a whole nother talk. But there's the USB HID descriptor tool that the USB Consortium publishes, so you can find this on their website. And it's a way that you can build up the descriptor, the device descriptor for a USB device that you want to create. So like this is an example for how you would build up the descriptor and then all the bytes that you have to put into to that USB endpoint to make it work. And that's a tool that'll help you do that. So I've spiked this out a little bit at amclean/joystick test. It's working right now on Linux. For some reason, it's not working right on Windows, which is interesting because HID is supposed to be just a general human interface device spec that works across a bunch of stuff. So anyway, got to debug that. And also over on the Zibo project for the Nerves keyboard we're building out, we're leveraging the HID keyboard driver, or HID keyboard device. So if you want to see how that works, we got a link over at Elixir Seattle/Zibo, and you can look at how we do the device descriptor there. So onto the deep dive of shift registers then. I've got all that GPIO that's coming in, and you saw that giant rat's nest of wire, and I basically ran out of GPIO pins on the controller. So with GPIO, you have to wire every single input and output, like every single button and switch or like LED or whatever. Each one of those components needs to be connected directly to one pin on your controller. And if you have a lot of those, like you saw in my project, you can start running out of pins pretty quickly. So rather than having to like add on a second controller to the project and try to synchronize those or something like that, one way that you can get around this is to start moving towards shift registers. And these basically act as like I/O expanders, is another way to think about them. So you can start tying each one of your components to one of these pins on a shift register. And your shift register really only needs like 3 lines coming back to your microcontroller. So you can really, really simplify the wiring back to your controller by doing this, and then daisy chain as many shift registers as you need together to be able to break out the I/O that you need. At a high level, there's 2 types of shift registers, input and output. They do pretty much what they sound like. So on the input side, you'll be taking buttons or switches or other kinds of inputs, which is basically, you could also think of this as parallel data coming in. So these are like 8 different bits coming into the shift register in parallel. What the input shift register is then going to do is convert that out into a serial data stream to the controller. And the output shift registers then do exactly the opposite of that. They'll take a serial data stream and convert it to a parallel data stream that you can then hook, each individual components up to, like LEDs here in this case. So the way that these work at a high level, you can find this kind of information in the data sheets, but I realize some of this information might look a little cryptic, especially if you haven't dug too deep into the electronic side. So I'm going to try to explain this kind of more towards programmers, so you don't have to be an electrical engineer to figure this out. So we'll go over the block diagram here, the functional diagram of what's going on, and there's two major parts to a register here, and we're going to look at an output register, but it's basically just flipped. The data just goes the other direction if you're dealing with an input register. And we've got the this shift register part up here that we're going to be clocking that serial data into. Then we have a storage register that's going to take the data from this shift register and like set it or store it. And that's going to, that data then is going to go out each one of these pins. So you can kind of think of the output pins as connected directly to this storage register. A lot of the registers also have like this 3-state output, so you can flip all the pins on or off. I'm just going to ignore that for the sake of this presentation. But it's a nice little feature if you want to like completely disconnect your controller from these outputs. You can do it with this pin, but for this, we'll just pretend this doesn't exist and that all these are just wired directly to the storage register. Also, if you need to know what each one of these cryptic names does when you see like DS, you can find that in the data sheet too. So like DS is serial data input. So those will make some of these names a lot more understandable. So the three that we're going to be dealing with here are DS for the data input, SHCP, which is the shift clock basically coming in, and STCP, which is the storage clock coming in. And I'll show you what those do. Also in the data sheet, you're probably going to find what might look like an intimidating diagram here at first glance, but I'll just try to make this pretty simple. You probably don't have to know this diagram to actually work with the registers, but it's in the data sheets, and I'll just try to simplify this here. So kind of ignore this stuff going in, but you've got like the data line coming in, clock line coming in, and the, shift clock coming in, storage clock coming in. And we've got these things that you're seeing here. These are D-latch flip-flops, which sounds like a big term, but I'll break this down into calling them 1-bit storage. So each one of these stores 1 bit. It can only be 1 or 0. And then there's just a lot of these cascaded through this chip. So you get a total of 8 of these stages. So this one is wired to another one, that one's wired to another one, and so on. So it's just the same thing over and over again. So as you're sending data into one of these storage registers, if you put a 1 on this data line, you then send it a clock pulse, and it will store the 1 inside this storage register. And a 1 will show up on the output here. Q is the output. Then if you put a 0 on the data line and trigger the clock, you'll have a 0 in this register. And since the first one here is tied to essentially the next one in the chain, when you flip the clock, the 1 will hop to the next one. You'll now have a 0 in here, and so on. So as you're clocking your data in, your data, each one of your bits is kind of hopping from register to register as you're triggering that clock. Once you've loaded up your shift register bit here, the way you want it, you've clocked in all 8 bits of data, or if you've cascaded these, you've clocked in all of the bits of data that you want. You've then got this connection here that's going down to the storage part. And here, each one of these bits is connected to the same stage. And the output of this storage register is connected right to the output pin, that parallel output pin there. So as soon as you send a pulse to this storage clock, it's taking all of your data from the shift register part, putting it into the storage register, and those values are able to come out the outputs of the chip. So this is kind of what the waveforms look like, and then I'll show you how this looks in code. So if you have, for example, this little binary stream here of like 1010, so on, you send a clock pulse in for each one of these bits into this shift register stage, and you send each one of these bits of data into the data line here. And once you're done clocking in all of that data at the very end here, you pulse that storage line to the storage register, and then you'll have this data that you put in serially, it will come out in parallel on each one of these output pins. So to get this working in code, Elixir code specifically with Circuits GPIO, we've wired up I/O pins to the data line, the clock line, and the storage register line. So we're going to loop through each one of those bits. So we've got 8 bits that we're working with. We're going to mask out the first bit, and so just kind of like take the first bit here. That's what that mask is doing. We're going to put that into the data pin, whatever that value is, 1 or 0. We're going to trigger the shift clock on and off. So that's what's going to give us one of those clock pulses. Iterate that through a bunch of times until we've done, oh, sorry. And then the other thing we're going to do before we end is we're going to, since we already captured the first bit, we're going to shift that bit. We're just going to like bump it off the stack, if you will. So that in the next iteration of this, the first bit we take is the next bit in the sequence. So this bit, this part here, this loop is just loading up the shift register full of data. Once we've got it loaded with data, we pulse the storage clock on and off, and then that's going to send those values out to the parallel pins on the shift register. So here's what that looks like in practice. And I've only got 4 of the 8 bits wired up here, but it should still show a good example here. So I've got the 3 lines coming in from the GPIO from the BeagleBone. I've got these color-coded according to the waveform on the scope here too, so you can kind of see what's going on. And here we've got pins Q0, Q1, Q2, and Q3 coming off the shift register. And then you'd have your remaining 4 bits kind of coming off the side here if you were using those. And you can see on the waveform here the data that was shifted into the chip from the BeagleBone from that code that I showed you previously. This is happening in reverse order on the waveform, so I've clocked the data in kind of like backwards from how you see the LEDs arranged, but that's all good. So blue line here, you can see those clock pulses of the shift register. So that just looks like that waveform for to clock in each of the bits we want. Every time this happens, it's going to take the value of that data line. So Q3, for example, is low, so this LED is off. Q2 is high at that point when that clock pulse triggers, so Q2 is on, and so on. And then at the end of shifting all the data in, we pulse the store line, and that's what actually gets the bits from the shift register out to the LEDs. And so I've got this source code around that you can play around with too. I'll link that at the end of the presentation. So one of the pitfalls that you can run into when using GPIO, I've seen this explained in the circuits.gpio documentation, and a lot of people describe these problems, but I haven't seen too many resources actually break it down into like waveform diagrams and something that you can actually see. So I just wanted to get a couple captures off the oscilloscope so that you can actually see what it looks like when you're working with pulsing pins with GPIO. And one of the big things is you can deal with inconsistent timing issues when you're doing this. So just using the cursor here on the scope, if you see the distance between these two edges of the waveforms here, this one happens to be 23 microseconds apart. The next one, if we measure those, is 19 microseconds, and the one after that is 18 microseconds. So there's kind of this little bit of distance between each pulse. They're not perfectly timed. And so depending on your application, when we're just turning on some LEDs here, that might be perfectly fine for this use case. But if you were trying to do something like robot control or something, really, really meticulous, where you need these pulse width modulation, for example, anything that takes that, where you need to be really specific about the pulses coming out of your pins. Triggering GPIO from an application level is probably not good for those types of use cases because you don't really have control over when these edges are going to happen. You've got to go from your application basically through to the kernel that has to talk to a driver that has to go out the pin. And in between there, you have the Linux operating system, and you also have like the Beam working to schedule other applications, other things that need processor time while you've requested your GPIOs to do things. So these SKUs may not be so bad here, but even just in running this same example, just leaving the scope running for a little bit, I was able to capture some oddities just in a really basic setup with this exact same code, this exact same little spike here. And so you can see these little oddities like this happen, where we're down here at a 50 microseconds per division between ticks here. So this is like a 250 microsecond gap just from the same code of when I asked a pin to turn on, from when the app requested that to happen to when it actually happened. So you can have weird things like this go on if you're trying to trigger GPIO from your application layer. This is another thing too, where if you've heard about like real-time operating systems, that's where that's their big thing about guaranteeing timing. Where that kind of stuff comes into play. So if you're dealing with a real-time operating system, for example, you're going to have stronger guarantees of knowing that the delay from one thing happening to another is there's going to be like a guaranteed amount of time that your process is going to get in processor time. And in a certain amount of time, you'll be able to loop back, your task will be able to loop back to do what it needs to do. And some other task isn't going to be able to starve your process from CPU time. So it gives you some more guarantees around what's going on here. Linux, of course, is a preemptive operating system, so you don't have those guarantees, which is why when you send something off to Linux, you can its scheduler can do whatever it wants and schedule your app to run in whatever process time it feels like. So you're kind of at the mercy of whatever it wants to do here for some of that stuff. But if you run into that situation and you're using something like Nerves, or you're using some kind of Linux-based system, you could farm any of those dedicated tasks out to like a dedicated microcontroller. And the BeagleBone Black, for example, comes with 2 PRUs, Programmable Runtime Unit, I believe it's called. And those are essentially 2 little microcontrollers in the die of the BeagleBone Black chip that run as dedicated microcontrollers you can compile code to. So if you need to use that, just a little point out there that it's something that the BeagleBone Black does offer built in, which is kind of cool. So then how do you wire this type of thing up if you want to if you don't want to use GPIO to trigger your shift registers? Another way that you can do this is to wire them up to the SPI bus. And you can use like circuits.spy instead of circuits.gpio. And you can use your SPI pins on the controller to be able to drive these shift registers instead. A cool part about this is SPI is basically a communication bus for embedded chips to talk to each other, like on a circuit board. But they're electrically compatible with shift registers, which is pretty cool. So in SPI, you get a certain set of pins here. You get a CS pin for chip select, you get a clock pin, and you get serial data in and out. And those happen to be electrically compatible with wiring up the chip select pin to your storage clock. So when the device wants to talk to, when your controller wants to talk to a SPI device, it triggers this chip select pin. So great for when we want to actually be able to load the data that we put in here into the components on the other side of this. The SPI clock happens to trigger every time a bit of serial data goes in or out of the system. So we can wire that right up to the shift register clock, and data goes to data. And that will clock in your data and then also trigger the storage. So cool little way to kind of hack SPI into driving shift registers there. So if we take that into code, couple things to know about if you're doing this versus SPI. The cool thing about it is you can now send data directly to a Linux device file. So just in the dev directory, you'll see, let's see on the BeagleBone, I believe it's called SPI dev, and then it's got some numbers for which SPI device you want to actually talk to. So you can open that up and just write data, read or write data to that file. And circuits.spy helps out with that. And the SPI driver in Linux will just take care of the rest for you of triggering all of those pins. So that GPIO code that we had down here in the application turns into SPI.transfer if you're using the circuits library, and you just push that the value that you want, and it'll take care of toggling all those pins for you, which is really cool. So looking at that on some of the waveforms, back in kind of the resolution that we were at before, you can see that SPI is significantly faster than working with this through GPIO, because we can just push that data out to the driver, and the driver gets just all the kernel time to, dedicated kernel time to go process each one of those bits, and it's able to go do it pretty quickly. So where we saw all that cycling with GPIO here before, keeping a similar time frame, all that SPI data just got, you can't even see the individual bits anymore in the same time scale. It was able to pack them so closely together. So a whole lot quicker to do that. And the timing between like the clock pulses here, for example, you can see we're now at 520 nanoseconds, so significantly faster. And you still don't have like real-time guarantees or anything doing this, but just looking at the waveform, you can see the clock pulses look significantly more consistent than they were in the GPIO diagrams. So cool stuff here. And if you want to check out this code, I've got the cockpit code up here. All the links in this presentation are clickable, and I'll link this out probably in the Nerves Slack channel. So cockpit code is there, and the shift register code is down at that link there. So this being said, any questions?
That was a great presentation.
That was great, yeah. Well, at first, you definitely explained one of them that I had, which is where do you buy cockpit control panels that are screen printed? I was really curious about that. One thing is that about the custom system that you had.
Yeah.
I was curious if any modifications to the system needed to be made out of, aside from the ones that were required to be able to get the config pin or the universal I/O device tree stuff working? Or was it just in pursuit of getting config pin working?
A lot of it was config pin. So now that I know what to do there, and also once I actually get this thing switched over to using shift registers, SPI is exposed on the BeagleBone Black out of the box, which is really convenient. So I won't need to set all of the pins into GPIO mode either. So I think by the time I kind of go through this refactor, I probably won't need a custom nerve system anymore, which will be pretty cool.
Well, so what I was thinking in that case was that if the only reason that you needed a custom nerve system was to get the config pin utility to function properly, I would consider that a bug in the upstream nerve system. And work that you've done for that custom one could easily get applied back upstream, because I'm a strong believer in that that universal I/O utility functioning out of the box.
Yeah, I have another question for you around that actually as well, because I thought about that, and the other route that I was thinking is I have a feeling that ultimately config pin might not be necessary if either basically if similar type of functionality was supported out of the box, or sorry, from a library. So like if like maybe something in circuits supported the pin configuration, like how circuits GPIO already supports it for Raspberry Pi, like maybe if that supported some kind of config pin options for, like it wrote to the correct paths for BeagleBone or something like that, or maybe just called a if there were like a replacement for config pin that were a dedicated like Nerves BeagleBone Black library, if like circuits.gpio just kind of like wrapped that for the BeagleBone case.
Yeah, I think that's an alternative method as well. And actually, now that I'm thinking about it, the reasons I believe that we kept marching down the supporting config pin route versus doing something native in Elixir was because of, I think it was the last time we touched this was pre-OTP 22 days. Where 22, 21, right in that area was when device file support was added for the in Erlang. At that point, then it made the story to be able to support that natively in Erlang a lot more desirable, because you could actually modify those kinds of special files. So you weren't able to do that pre that version of OTP. Now that the dust has settled, and as you know, mostly all of us in Nerves projects operate bleeding edge Erlang and Elixir.
Mm-hmm.
I think that mostly everybody in the community is probably likely on a version of OTP that's greater than that 22 or 23.
Gotcha. Okay, cool. Yeah, if the config pin route supporting that's the option you like, then yeah, that gives me a good thing to keep in my mind. Then a good route to go for that.
Yeah, I think that would give us immediate support, at least, which would be nice.
I have a question.
Yeah.
And I don't know if this is for you, Alex, or this might be for Justin or somebody else, but on the Raspberry Pi, there is pin 18 is the one you're supposed to use for pulse width modulation. But I thought the Pi didn't really support true PWM like Arduino does. How do they get the clock to work?
So in that case, it's run through the DMA controller. Yeah, it's the some really low-level memory that's set aside for some more mission-critical tasks inside of Linux. I believe that in Raspberry Pi, that controller is sharing the same clock source as the SD card. And so from my experience in the past, I've seen that if you were to use that PWM pin on the Raspberry Pi to, for example, light up and blink a bunch of tiny little lights, that eventually, if you do that fast enough and long enough, or I should say even if you animate that hard enough, that you'll start getting SD card read timeouts. So that's my understanding of how they get away with that one.
Okay, and one more question, Alex, is when you showed those other cockpits, that one dude had that 180-degree screen. What's the hardware for that? I couldn't tell if that was a curved monitor or if that was a hologram or what.
If I remember that one right, I think he has projectors set up, and that he's doing, I think, edge blending between the different projectors to get that working.
Yeah, and the follow-up on that one too, on your version of the cockpit, you also had mimicking screens for some of the output control. Is that also coming through the BIOS system as streaming data, or?
That one is not. That one is an Adventure and DisplayPort. So that's probably a whole nother talk right there. But yeah, I essentially had to hook up 5 monitors to the computer to get that working, essentially. So that's a bit of an adventure.
You might be interested. Very recently, I finished a task for a client to be able to get the graphics accelerator working on the AM3358, the BeagleBone processor.
Mm-hmm.
And so there's an LCD controller on that you can actually hook up 24-bit RGB, up to 24-bit RGB LCD displays.
Oh, really?
Operate those as video panels. So maybe if you could capture frames or something over UDP, if you could stream some of those panel informations out, you could probably blast that to that panel.
So there's another really interesting use case for that too. Some folks are using iPads and stuff like that, basically tablets for just extra controls. If they want to be able to get to stuff, they'll just have some virtual buttons hooked up on that. And if you hooked an LCD screen up to the BeagleBone, for example, you could use Scenic or something like that to keep it all in the same system without having to bridge out to more devices that you cobble together and hook into the same software. So that could be really cool. That's an interesting idea.
So you didn't have to get into the analog world for any of this with Nerves?
I did a little bit. So I had to set up the ADCs. If I go back to, let's see, one of these slides here. Here we go. So some of these knobs are analog controls, and I rigged those up to the ADC pins of the BeagleBone.
Okay.
Yeah. So I got a little bit of the code that's just kind of sampling those on a loop, and it's just spamming that data out to the computer, basically. So those will move in the cockpit too, and that's really cool. Being able to set the trim and stuff there is a whole lot easier.
Oh, now it makes total sense on why I got RTFM'd with Frank on the ADCs, and you uncovered that for me.
Yeah, this is exactly how I knew how to configure the ADCs, because I just had to go through it in this project.
I'm wiring mine up to a dumb temperature sensor.
Gotcha. Actually, that was the funny. That was project number 2 that you saw here. So. Yeah, this thing was the little temperature sensor board that had to be read back in through. Actually, no, this one was great. This temperature sensor was SPI, so that made my life easy. Never mind.
So I've used OshPark before, but I've never used JLC PCB, but I've heard really good things about them. And they claim to have a pretty serious, pretty seriously fast turnaround time on these. In your experience, what is the quickest you can get a turn on like 5 boards of this?
So I'm in the same boat as you. This one I actually did through OshPark, but their configuration tool, of course, doesn't look as doesn't have as many options of this as GLC PCBs. You get they're kind of like the Henry Ford of PCBs. Is you get any color you want as long as that color is purple. So OshPark purple. So I actually did this particular board through OshPark, and if you saw that screenshot that I posted in the Nerves channel, that purple board is this board. So I haven't used JLC yet, but I want to. So as soon as I do, maybe I'll have to give an update on like what their turnaround time is and what their service is like.
It feels like Osh. You're like stuck with like weeks delivery, and then your expedited one is still only guaranteed for like maybe a handful of days. But JLC seems to be like able to. They're almost even saying like same day or 2-day turnaround.
Huh. I feel like I should look this up. I feel like my OshPark boards came in within 2 weeks. I feel like it was more like 1 week, but I'm fuzzy at this point.
I have a toy, some goodies to share following this that we can geek out about them.
Okay, cool.
I got a question for you. You briefly mentioned your like 20 millisecond debounce hack. Can you or other folks explain the circuits debounce support, if any, and how you compare it to the debounce hack? Because I think I'm going to run into the same problem here pretty soon.
Yeah, I just asked about this before the presentation to try to keep it out of the presentation, but I'll give you the TLDR of kind of what I learned here and what the summary sounds like, and if Mark wants to add to it, by all means, feel free to jump in.
Probably not.
Okay. So what I've learned, because we have this problem in the Kibo project too. When you go to Circuits GPIO, there's an option to be able to set to turn your interrupts on. And if you're using interrupts, there's supposed to be a way, the interrupts are supposed to debounce for you. There's an atom that you can set to do debouncing. The catch is it's an atom. It's not any kind of value that you can set a debounce time. So in my experience using it, actually, let me back up. There's one other caveat. If you're dealing with GPIO pins and interrupts in microcontrollers, like non-Nerves microcontrollers and stuff like that, in the documentation that I've seen for those, they say do not use interrupts for like UI stuff. Like don't use it for buttons. Use it for like chip-to-chip communication, where you're not going to have a bouncy signal. So from the Circuits GPIO standpoint, when I was digging into what it's doing, it looks like it forwards the kind of like the debounce setting. It looks like it forwards that through the NIF to the kernel. And I haven't been able to dig in anymore yet. I haven't had the time to look at what's going on in kind of kernel space or on the driver side of what's going on. But So far I haven't seen a way to set the debounce time, and I haven't really figured out what magic it's doing under the hood or what the debounce value is under the hood or anything like that. So just for the sake of getting this project done, I found it was just easier to just implement my own little polling timer here and call it good. But if you need to use the circuit's GPIO interrupts for this, I'd say you'll probably have to dig through some of the Linux documentation and figure out what's going on with Linux GPIO.
All right, thanks. I might actually do what you've done here, because what I've noticed thus far, for at least my application, for my little Roly bot here, it seems like the little IR sensors are triggered somewhat randomly by errant light or just sunlight kind of randomly. So
Gotcha.
debounce might not catch situations like that. But I really want is a little bit more of a blind robot.
Yeah, and if you're using Elixir's Bitwise module, then this is really easy work with just being able to XOR the last value that you read to be able to tell if it switched or not. And yeah, I've got some code in this project to do that, so feel free to steal code from here if you need it.
Probably will. Thanks.
When you do this, you're just using one of the, either high to low or low to high interrupt?
I'm not using any interrupts when I'm doing this. I'm doing an initial, so I'm doing an initial pin read to find all of the initial values. And then I'm doing let's see. Let me hop into GitHub. Oops, that's not GitHub.
Okay, so you're avoiding the interrupts altogether here then?
Exactly.
Ah, okay, that's fine.
Okay. Yeah, and then so I'm just reading them in that timer handler.
I see. Okay.
Grant, can I ask you a question about your robot?
Oh yeah, I'm very far along, as you can tell.
Oh well, I've got I had an idea for a project that's not that dissimilar from it, but I was curious as to why you chose the IR sensors. Like I've never used the IR sensors before, so I wasn't sure if they had advantages. Like for distance, I've always used the ultrasonic sensors. So what are the properties of the IR sensors, I guess?
I didn't think through it too much, as opposed to like the sonar ones, the sonic ones. In my case, when I was a kid, I built a bunch of robots that had bumpers on it, and I got sick of things running into stuff all the time. So I figured if I can avoid a bump, that would be great. I didn't get much further than choosing IR.
Okay.
I don't know. Obviously, things that are more reflective seem to work better. It still seems to have a hard time with like dark wood paneling or like a dark sofa or something like that. I know Sonar has a hard time with sofas too, but maybe it's better now.
Oh, okay, so Sonar is bad for soft materials, whereas light would not be affected necessarily by the softness, but it is affected by the darkness. So I guess that's maybe a good case for using both.
And IR is, of course, just totally useless outdoors because there's just way too much light.
Mm-hmm.
Okay, that's a good reminder for me, because the thing I was looking at was going to be outdoors.
Do y'all have any examples or recommendations for what I should look to for examples of how to organize my code for a little bot like this? I kind of want to do it with a little bit of intention. I could probably put it in one big file for as simple as it is. It basically is run around, don't run into stuff. But I'm kind of curious as to what sort of examples might already exist for a little couple-wheeled bot with some sensors.
I think my general recommendation would probably be like try to break down the code by like components or functionality. Actually, I had another talk. It's sitting up on YouTube. Let me try to pull it up on Google Drive or the presentation up so I can just get the slide I'm looking for. And I kind of showed in this how to do some code architecture around these types of things. Here we go. So this was a NURBS-powered solder reflow toaster oven. And it had a couple things, and I kind of broke out a little bit of architecture here. It's not a really complicated project, but maybe this type of thing helps, where you've kind of got like all the nerves and circuits used to be called Elixir Ale at one point, so that's what this layer is. And I kind of broke things apart into like, oh, I need these buttons to do certain things. I have, so like these are my inputs. I've got relays that are my outputs that I need to control. I've got thermocouples, and those are sitting on top of a SPI bus. So like I need to talk to this SPI bus and get arbitrary data out of it. I can send that up to a layer that specifically knows how to decode the thermocouple data that's coming off of that bus. And then there's just like this controller layer that bridges all these together. So if you press like the start button, it knows the controller receives that button event and then turns on the relays and starts monitoring from the thermocouples and such. So if you can kind of figure out how to break your system down into like different components or different systems of like your hardware, both like physical hardware and then like logical functionality, that might be a way to approach it.
You think it is probably a good pattern or more of a anti-pattern to say like this gen server is responsible for this set of buttons, or this button, this gen server manages motor controller?
I think that's a good pattern.
Yeah, I would say probably like the way I did it here is group of buttons. In that way, what you can do is open up. Oh, do I have the code in here? You're going to make me give the whole other talk if I dig into this presentation. So I'll try to explain it simply. So like some of these groups of buttons, I could just open up all those in one. I could open all those GPIOs up in one gen server. So they were all happening in the same gen server loop, because you don't want to bog down your gen servers, with, you don't have to message pass between gen servers too much. So, like everything that dealt with the UI buttons coming in would receive those circuits messages just back to that gen server. The oven relays, these might not have even been a gen server because they were just outputs. I'd have to go back and look at the code. If you want the code is here. So that'll end up in this presentation, so you can get to that link. Because those were just like some I/O pins that needed to be just like turned on or off. So that module didn't have to deal with receiving events. So you can kind of structure things like that. Like gen servers are really good for things that need to receive messages and process things based on messages happening. Whereas if I go back to that architectural diagram, the controller layer, for example, would be a gen server, like receiving events from the buttons. But if the oven relays are just either on or off, like the controller can just send, they can just call these functionally, and then that pin will just flip on and off functionally. So you can just leverage those CPU cycles happening in the controller process rather than having yet another process that your system has to manage.
Cool. That makes sense. Thanks.
Yeah.